Hello everybody, welcome to this video tutorial on how to monitor oil spills using Sentinel-1 satellite images. Hope you are doing well. My name is Muhammad Ramadan, and through this video I'll try to guide you to identify the problem, how to get data and do the processing and GIS calculation all in open source software. The main objective of this training video is to introduce you to one of NAV cost project services, which is the oil spill monitoring using sensitive aperture data. Also, you will see how these SAR data provide advantage over the conventional optical sensors in the oil spill mapping. Then we will explore two case studies from Egypt and how it can be mapped using SNAP and QGIS. Before we finish, I'll introduce you to the Sentinel Earth Observation Browser and Data Hub to explore multiple data on the cloud. NAVCOST project is funded from European Union and African Union Commission through GEMIS and Africa program to serve the North African countries. This project aims at providing coastal and marine services and thematic maps based on in-situ measurement and Earth observation data. NAVCOST has identified three main services to be developed. First one is mapping the oil spills. Second application is to provide maps for the potential fishing zones. And finally, building human capacity for these two services in the participant African countries. The project is coordinated by the National Authority for Remote Sensing and Space Science in Egypt and has started with three partners from North African countries, which is Morocco, Tunisia, and Mauritania, in addition to the regional organization of SIDARI. The oil pollution problem is frequently seen in the marine environment, and it's mainly related to the petroleum activities, tanker accident, and shipping routes. The problem represents a serious hazard for the marine creatures and also affect fishing and navigation activities, so we have to monitor. Comparing the different sources of pollutants, we can find that deliberate oil spills in the form of controlled discharges from ships form more a major threat than large oil accidents and oil platforms. As most of them are small in size, quickly disappear in a few hours, and couldn't observed by regulating authority. So we must pay attention for the problem, as even small spills can cover large areas in a few hours, and it takes years for the environment to remediate. Compared with optical sensors, SAR is preferred for sea pollution monitoring. At working within the microwave range, the image is not affected by cloud nor weather conditions. More importantly, it works day and night, which gives the chance not to miss recording of any oil spills happening at night. Moreover, it provides a wide range of spatial coverage, which make it suitable for the oil spill application. And regarding the detection technique, it's known that oil is a viscous material, and where there is an oil film on the water surface, the capillary waves are damped. These capillary waves are damped. This reduces the backscatter for the radar sensor, so it forms dark pixel as that appearing in the image on the right. The dark area which represent an oil field. Now we will go briefly through our first case study, which is from Port-Said city in Egypt, north to the Suez Canal. That area had a dense marine traffic due to the canal, and one of the largest accidents happened there on the 4th of October 2014. The task is to identify the profile of the spill and to make it in a GIS layer as shown in the next slide. Moving from left to right, we can see how the original raw data have been processed to enhance the contrast, and then the dark area have been masked for further GIS calculation. It's a pretty simple exercise, so let's move to Snap to know how to do this processing. Snap is the Sentinel application platform, and it's open source software, so you can install for free. I have downloaded the data, and further in the video I will show you how to get this data. To open the data, navigate to it on your hard disk, and We can see that it contains 4 bands, VH, amplitude and intensity, and the VV is the same. We are interested in the amplitude VV band for the oil spill application. The intensity band is the square of the amplitude. So here in the navigation band, we can see that dark area. It's geometric pattern, and other parameter can judge that, can help you in judging that this dark area is an oil spill, as there are other lookalikes which maybe look dark in the image but not an oil spill. The first part of our exercise is to subset that area. So raster, first we have to select raster, subset, and you give the coordinates upper left and lower right. I have identified it from here to here. So that is my number. Okay, that the subset part is number 2, has index 2. So you see it. Here is our subsetted area. You can see that there is bright and dark pixels, which is the problem called the speckles related to the SAR image. To solve the problem, we have speckle filter. So radar, speckle filtering, single product speckle filtering. We are using the low sigma, so it's leave it all as default and run. Yes. The result is index 3 to see the result and to compare tile horizontally. We can see here and here the difference in the speckle. If you go zoom in, you can see how this area dark pixels have been smoothed with the dark ones. So we can make more contrast for the image by converting the normal data to decibel range, linear to decibel, scale, and run. Here is data in the decibel range. Radar data have very low values and the very high values, so displaying in decibel scale, it gives better contrast. And for that image, we can see how the profile appear. We can plot this profile and do analysis, profile plot, and see the difference in the backscatter for the image. We can select. We can see that any point here appears in the screen, in the location of the screen. So that is the normal seawater surface reflectance, which is mainly normally 20, and the dark area have a back reflectance of 16 or 16.5. So the difference is 4 decibel between the dark area and normal seawater, and we will use this value in the detection. So now we have to go to the oil spill application. From radar, SAR application, ocean application, oil spill detection. Snap has a pre-made toolbox for doing the processing of the oil spill detection. You have to give it the input, which is the index 3 here, and through different tabs we are interested in the VV band and the oil spill detection only VV band. Here is the threshold we will give for the program to extract the oil spill mask. We are using for the background window size a value from 1000 to 1015, and the threshold shift we are using 3.5 decibel. These values are up to your application. You have to run and see the result. If you are satisfied, it's okay. If you are not, you can change these numbers and do the processing again. And we are locating the output. Here is our case. Select. For that step, it takes large time, so I will not do the processing. I just open the result. Here is the result of the oil spill detection, and here is the bands. That is my result for the detection. The software extracted the dark area as a separate mask, and to match, we can change that color to red and add it to this layer. So we have a good result here. Layer manager. So that is the overlaid image, the mask and the original image. We can see the quality of the masking. Here is some areas not masked. That is based on the threshold number we gave for the oil spill detection toolbox. The last step is to do the geometric correction. That image is reversed, as you see, because of the detection of the SAR sensor. It takes a reversed image, so we do the geometric correction, radar, geometric, ellipsoid correction, geolocation grid for that layer. We are giving the oil spill detection and doing the map projection automatic to identify which part of the world. Here is the UTM zone 36 and run. After determining where is the output, and do running the geometric correction. I have run it here, and that is my result. You can see that is the image, and that is the reversed image after geometric correction. So now we can export this as a GIS layer, raster data conversion, band select. I'm selecting that mask and saving it to my folder, mask. On. So that is the result for my case. Here is the test layer, and my task now is to calculate the area by moving to QGIS. So that is the interface for QGIS, new project, and loading my layer here. You can identify that the value of the pixels here is 1, here is 0, and here is intermediate values. My task now is to extract all the non-zero values to a shape file. So the first, I have to convert this raster to polygons of each pixels. Raster pixels, 2 polygons, and the output will be value, name, then we have to extract only the non-zero values. So we are using extract by expression. That is vector layer, and our expression that value not equal 0. Okay, and run. Open the matching feature for a temporal layer. Then we are dissolving this feature. And here is our result. That is the extracted layer. And to calculate area, we are open attribute table and edits. Here is field calculator. Create new field area in decimal number. Okay, that is the expression for calculating area, and we are dividing 10 to the power of 6 to calculate in square kilometer. Okay, and here is the result. 27 square kilometer for that oil spill. So that is the most important for our case, is to get the area of the spill, and we can save it as the shape file and do mapping and all GIS calculation. Now you have a vector layer. After we finish the QGIS part, we now explore the Earth Observation Online Data Hub for browsing data before we download it. ESA provide an online application for browsing data. Here is Sentinel-1, and we can search, visualize. We are visualizing SAR data in the VV decibel gamma Orso rectified band. And for Egypt, we have multiple cases happened. One at 21 2019 of May. Here in Alexandria. That is a too long tail of dark area and a head of bright area, which is a ship. So we are identifying a case for a ship that's charging while movement. Another case at 2020, June 17. Here, also a ship. And you can explore multiple cases before you download through that application. You can create a GIF of multiple images at the same location to explore data before you download. And once you detect the case, you can download it from the ESA hub just to identify the area and the sensing period, satellite mission, Sentinel-1. We are using the GRD, product type, and sensor mode IW, interferometric wide swath, and then search. After deciding the range, time range, Here is the scene if you are interested, and just download. So going back to slide with our next case, we are seeing now another case from Egypt, also on the 21 of May 2019. This dark patch have been detected near Alexandria from Sentinel-1 image, and we can see a bright spot at the tip of the dark tail, which is a strong proof for a moving chip discharged during its movement. So going back to Vessel Tracker AI's data, we could find an excellent match between a ship path and the oil pollution line at the same place after converting to a GIS layer. So requesting that ship information, we could identify its details. Here is the profile of the ship, and here is our pollution that we have excellent match through marine traffic website. So that is the ship responsible, Armada Pride, and here is all its details. So now we can give a proof for the regulating authority who is responsible for the pollution. Now we can see how NavCoast project works on activating the Earth observation application in the African community by providing precise information to decision makers. The project as well welcomes all engagement from the local communities to spread its services. Moreover, we could discover how the availability of Sentinel-1 satellite data is an important source in developing the oil spill monitoring application. And training knowledge dissemination is essential to spread the application. You can review the full case for the pollution we have introduced in the slides through this paper. Finally, that's all for the tutorial. I thank you very much for watching and hope that you have learned something new today. I hope that you could find the application interesting for you, and you can follow our activities on the Facebook page, Twitter, and YouTube. So I'd like to thank all of the NavCoast project team. Thank you all. Thanks.